Something is wrong with reality. Not metaphorically, not philosophically. Physically, mathematically, experimentally wrong. And the evidence has been confirmed to a precision of 1 part in 10 billion. The universe, at its most fundamental level, does not behave like a universe should. Objects do not exist in fixed states until something measures them. Particles travel through 2 places simultaneously. The past can be altered by decisions made in the present. And somehow, in a way that no one has yet been able to fully explain, the act of observation, of simply looking, is what collapses the haze of possibility into the thing we dare call reality. This is not a theory anymore. This is not fringe science whispered at the edges of academia by people who have had too much coffee and not enough sleep. This is the most tested, the most verified, the most mathematically precise framework that physics has ever produced. And it is telling us, in terms that no longer leave room for comfortable denial, that the physical world around you is, in some profound and genuinely disturbing sense, not fully there until you interact with it. Let that sit for a moment. Everything you can see right now, the room around you, the device in your hands, the objects sitting quietly on shelves and tables, all of it presents itself to your experience as something solid, defined and continuous. You leave the room, you come back, and the chair is still there. The coffee cup has not teleported. The laws of cause and effect march on in their reliable, comforting procession. This is the world of classical physics, of Newton's apple falling from the tree, of Einstein's elegant relativity bending space-time like a rubber sheet stretched across the cosmos. It is the world that makes sense. But beneath it, at the scale of atoms and electrons and photons, at the very foundation of everything that the table and the chair and you yourself are built from, something else is happening entirely. Something that has made even the greatest scientific minds in human history stop dead in their tracks and stare into a darkness they could not dispel with any equation. Albert Einstein spent the last 30 years of his life fighting it. He called the implications spooky. He insisted the theory had to be incomplete, that there had to be hidden variables underneath the madness, giving it all a sensible explanation. He was one of the most brilliant humans who ever lived, and quantum mechanics broke him. Not figuratively. He never solved it. He died still refusing to accept what the math was saying. Niels Bohr, the man who helped architect the theory from the ground up, once told a room full of physicists that anyone who's not shocked by quantum mechanics has simply not understood it. Richard Feynman, winner of the Nobel Prize and arguably the most gifted scientific communicator of the 20th century, put it with characteristic bluntness. He said he thought he could safely say that nobody truly understands quantum mechanics. And yet, the experiments kept coming back with the same answer. Reality does not exist in any definite form until it is observed. And now, in the 21st century, the experiments have become so precise, the loopholes so methodically closed, the results so relentlessly consistent, that we can no longer hide behind the comfortable excuse that we must be misunderstanding something. We are not. The universe is just this strange. Welcome to the rabbit hole. There is no bottom. Here is the thing about a discovery this big. It does not announce itself with fanfare. It arrives slowly, buried inside equations that only a few hundred people on the planet can read fluently. validated through experiments that require lasers and cryogenic chambers and detectors sensitive enough to register the impact of a single particle of light. It slips into the scientific literature with a title that sounds almost boring. And then one day you sit down and actually think about what the numbers are saying, and something inside you shifts permanently, because the question is no longer whether quantum mechanics is correct. That debate ended decades ago. The only question left, the one that physicists, philosophers, and neuroscientists are now tearing themselves apart over, is what on earth it means. To understand why reality behaves this way, you have to start at the very bottom. Not the bottom as we experience it, not atoms, not molecules, not even protons and neutrons. You have to go deeper, to the quantum scale, where the rules of the world you know simply stop applying and something alien and beautiful takes over. At the quantum scale, particles do not move the way baseballs move. They do not have a precise position and a precise velocity at the same time. This is not because our instruments are too clumsy to measure both at once. It is not a limitation of technology. It is a fundamental feature of nature. Werner Heisenberg was the first to formalize this in 1927. And the principle named after him states that the more precisely you know where a particle is, the less precisely you can know how fast it is moving, and vice versa. The uncertainty is not in your head. It is baked into the fabric of reality itself. But the uncertainty goes deeper than Heisenberg, much deeper. Before a quantum particle is measured, it does not just have an unknown position. It does not exist at a single definite location at all. Instead, it exists as what physicists call a wave function, a mathematical object that spreads out through space like ripples on a pond, encoding not a single definite state, but a superposition of all possible states the particle could be in, each one weighted by a certain probability. The electron is not secretly sitting somewhere specific while we are not looking. It is genuinely physically spread out across all the positions it could occupy, existing in all of them simultaneously. This is superposition, and it is not a metaphor. It is what the equations describe, and what the experiments confirm. The wave function is one of the strangest objects in the history of human thought. It is not a physical wave like a sound wave or an ocean wave. It does not carry energy in the conventional sense. It is a wave of probability, or, depending on your interpretation, a wave of pure potentiality. It describes not what a particle is doing, but what a particle might do. And as long as no measurement is made, as long as no interaction forces the particle to commit to a particular state, the wave function evolves according to a perfectly deterministic equation called the Schrödinger equation, spreading and flowing and interfering with itself in ways that are mathematically elegant and physically surreal. Then something extraordinary happens. The moment you try to find out where the particle actually is, the moment a detector clicks, a photographic plate registers a flash, any physical interaction occurs that could in principle carry information about the particle's state, the wave function collapses. All those shimmering possibilities condense instantaneously into one outcome. The electron, which existed everywhere in its probability cloud, is suddenly here, in this precise spot, with this precise value. The superposition is gone. Reality has been pinned down. And the mechanism by which this happens, the transition from quantum blur to classical fact, is called the measurement problem, and it is the deepest unsolved mystery in all of physics. What counts as a measurement? What causes the collapse? Is it the detector, the experimenter reading the result, the computer recording the data? Does the universe require a conscious mind to finalize reality, or is any physical interaction sufficient? Physicists have been arguing about this since the founding of quantum mechanics a century ago, and they have not agreed on an answer. Different interpretations of quantum mechanics give radically different answers to these questions, and remarkably, all of them are currently consistent with every experiment ever performed. This means the experiments can tell us what happens. They cannot yet tell us why, or what it means for the nature of reality at the deepest level. The Copenhagen interpretation, developed by Bohr and Heisenberg in the 1920s, gives what became the standard textbook answer. The wave function is just a mathematical tool for predicting measurement outcomes, and asking what the particle is doing before it is measured is simply not a meaningful question. Shut up and calculate, as the physicists say. This answer satisfied a generation of scientists busy building transistors and lasers and nuclear reactors out of quantum mechanics, without worrying too much about the philosophical implications. But it has always felt like a cheat, like answering the question of what happens in a forest when no one is there by declaring the question invalid. The many worlds interpretation proposed by Hugh Everett in 1957 takes the opposite extreme. It says the wave function never actually collapses at all. Instead, every time a quantum measurement occurs, the universe branches. Every possible outcome happens in separate, non-communicating branches of reality. When you look at an electron and find it spinning one way, another you in another branch of the universe finds it spinning the other way. Both are equally real. Both persist. The universe is constantly proliferating into an uncountable infinity of branches, each one as real as the one you happen to inhabit. This interpretation preserves the mathematics perfectly. It avoids the collapse problem entirely, and it is, by a significant measure, the most terrifying idea anyone has ever had. There are other interpretations: pilot wave theory, relational quantum mechanics, cubism, objective collapse theories, each one a different attempt to answer the same haunting question: what is really happening when we are not looking? Each one passes every experimental test. Each one requires a worldview so alien that it strains the human mind to the breaking point. The fact that physicists cannot agree on the right interpretation after a century of trying is not a sign of their failure. It is a sign of the magnitude of what they have discovered. Reality is stranger than we are built to understand. The story of quantum strangeness did not begin with equations. It began with light. In 1701, Isaac Newton published his particle theory of light, arguing that light was composed of tiny corpuscles, particles shooting through space like miniature cannonballs. Christian Huygens disagreed vigorously, insisting that light was a wave. For a century, the debate raged. Then, in 1801, a man named Thomas Young ended the argument with a piece of cardboard and a candle flame. Or so he thought. Young's double-slit experiment is simple in concept. You take a barrier with 2 narrow slits cut into it and shine light through. On the other side, you place a screen. If light is made of particles, you would expect 2 bright bands to appear on the screen, one behind each slit. But that is not what happens. Instead, you see a pattern of many alternating light and dark bands stretching across the screen. An interference pattern. The kind of pattern you get when 2 sets of waves cross each other and combine, sometimes reinforcing, sometimes cancelling. Young concluded that light must be a wave, and the physics community eventually agreed. Wave theory of light, 1. Newton, 0. Then quantum mechanics arrived and completely detonated this clean resolution, because it turned out that light is both. And here is where the experiment stops being a clever demonstration and starts being a nightmare. When physicists perform the double-slit experiment not with a beam of light, but with individual photons, single particles of light fired one at a time, so that only one photon is in the apparatus at any given moment, something impossible happens. Each individual photon is detected as a single dot on the screen, a discrete particle hit. Good. That makes sense. Particles land in spots. But as you fire more and more photons, one by one, and the dots accumulate on the screen, they build up into an interference pattern. The pattern that requires waves. The pattern that requires the photon to go through both slits simultaneously and interfere with itself. How does a single particle interfere with itself? The only possible answer, if you take the mathematics seriously, is that each photon travels as a wave of probability through both slits at once, interferes with itself on the other side, and then collapses into a point when it hits the screen. The particle takes all paths simultaneously. It exists in a superposition of going left and going right until the screen forces a commitment. But physicists, being the kind of people they are, wanted to push this further. They wanted to catch the photon in the act. They set up detectors at the slits, devices that would record which slit each photon actually passed through without stopping it. The photons could still go through, but now someone would know which path they took. And the moment they added those detectors, the interference pattern vanished. Gone. Completely. Instead of the multiple bright bands, they got 2 bands, one behind each slit. The moment the experiment gained the capacity to acquire information about which path the photon took, the photon stopped behaving like a wave and started behaving like a particle. The universe restructured its behavior based on whether information was available, not based on whether anyone was actually looking. This result has been replicated thousands of times, with photons, with electrons, with entire atoms, and even with molecules containing 60 carbon atoms. Tiny soccer balls of matter so large that they can be seen under an electron microscope. Every time, the same result. The moment a measurement is possible, interference disappears. The world snaps from quantum to classical the instant it becomes knowable. And then, in a move of breathtaking audacity, physicists asked what happens if you erase the information after the fact. The quantum eraser experiment is one of the most philosophically destabilizing things ever performed in a laboratory. The setup is a variation of the double-slit experiment in which photons are sent in pairs, an entangled pair, where what happens to one is correlated with what happens to the other. One photon, the signal photon, goes through the double slits. The other, the idler photon, goes to a separate detector. By looking at the idler, you can in principle determine which slit the signal photon went through. And sure enough, when you run the experiment this way, the signal photon produces no interference pattern. Knowledge of its path destroyed the quantum superposition. But then you route the idler photon into a special device that destroys the which path information before any human ever reads it. The information is erased. Not hidden, genuinely erased, gone from the universe. And the interference pattern comes back. The signal photon, which went through the slits long before the idler photon's path, information was erased, retroactively produces an interference pattern. The outcome of what the photon did in the past appears to depend on a decision made about its partner in the future. Time, causality, the orderly march of events from past to present. In the quantum world, these are not the iron rules they seem to be in the world we inhabit. John Archibald Wheeler, one of the giants of 20th century physics, pushed this further with his delayed choice experiment, first proposed in 1978 and experimentally realized in 2007. In Wheeler's version, the decision about whether to measure which path a photon took is made after the photon has already passed through the slits, but before it hits the detector. The measurement decision is delayed until the photon is already, by any classical account, committed to its path. Yet the results are the same. The photon's behavior, wave-like or particle-like, matches the decision that is made after the fact. It is as if the photon travels back in time to rearrange its own history to match the measurement that has not yet been made. Wheeler liked to phrase it this way: we are not merely passive observers of a universe that was already there. In a fundamental sense, through the act of observation, we participate in bringing certain features of the past into concrete existence. He called it a participatory universe. And before you dismiss this as poetic excess from an elderly physicist, understand that the experiment confirming it won the 2022 Nobel Prize in Physics. That Nobel Prize went to Alain Aspect, John Clauser, and Anton Zeilinger for their work on entanglement and the violation of Bell's inequalities. And if you want a truly airtight demonstration that reality does not exist independently of observation, this is it. In 1964, a physicist named John Bell derived a mathematical inequality that would hold true in any universe where objects have definite properties before they are measured, what physicists call local hidden variable theories. Bell showed that if particles carry preset values like hidden instructions determining their outcomes in advance, the correlations between measurements of separated particles can only reach a certain maximum level. Cross that level, and the only explanation is that the particles did not have definite properties before measurement. They genuinely did not. Aspect and his collaborators ran the experiments. The correlations exceeded Bell's limit, not by a little, by a margin that made any local hidden variable theory impossible. They closed loophole after loophole: the locality loophole, the detection loophole, the freedom of choice loophole. And with each successive generation of experiments, the result came back the same. The world is non-local and indefinite, Particles separated by vast distances are correlated in ways that cannot be explained by any pre-existing property they carry. They are connected in a way that transcends space. And before they are measured, they genuinely do not have definite values. Quantum mechanics is not incomplete. It is not hiding a more sensible reality underneath. The universe is, at its foundation, indefinite until observed. Perhaps the most eerie confirmation of all comes from the work of researchers testing large-scale quantum superposition. For decades, physicists assumed that while individual particles could exist in superposition, the quantum weirdness would average out at larger scales, that the classical world would emerge naturally from the quantum substrate through a process called decoherence. And decoherence is real. It explains why you do not experience yourself in a superposition of having eaten breakfast and not having eaten breakfast. But it does not eliminate the quantum indefiniteness. It hides it. It does not collapse the wave function in the fundamental sense. It merely makes the superposition enormously difficult to detect. And as experiments with increasingly large molecules, with tiny mechanical oscillators, and with superconducting circuits have demonstrated, quantum effects persist at larger and larger scales than anyone expected. The boundary between quantum and classical recedes every time we push against it. In 2012, researchers demonstrated superposition in objects containing over 800 atoms. In 2019, molecules composed of over 2,000 atoms, large enough to be extraordinary by any measure, were shown to undergo quantum interference. The frontier is being pushed with every passing year. The classical world you inhabit is not fundamentally different in nature from the quantum world beneath it. It is the quantum world observed and decohered and collapsed into the apparent solidity of daily experience. Pull that curtain aside, and the same rules apply all the way down, and apparently a great deal of the way up. Now stop and breathe, because if you have followed this far, you are standing at the edge of something genuinely vertiginous. The experiments are not ambiguous. The results are not in dispute. What quantum mechanics is telling us about the nature of reality is clear enough in outline, even if the interpretation remains a battlefield. And the implications of that outline are staggering in ways that reach far beyond physics. Start with what it means for the concept of an independent reality. For most of human history, and for the entire span of classical physics, the assumption has been bedrock. The world exists out there, independently of us, doing what it does, whether or not we are looking. The moon hangs in the sky when you are asleep. The atoms in your wall vibrate in their lattice when no one is in the room. Things have properties, position, velocity, spin, all the time, whether measured or not. This assumption is so deeply woven into ordinary experience that challenging it feels like madness. But quantum mechanics, and specifically the experimental violation of Bell's inequalities, demonstrates with the force of mathematical proof that this assumption, which physicists call local realism, is false. The world doesn't have a complete set of definite properties independent of measurement. Particles do not carry hidden instruction sets determining their behavior in advance. The correlations observed in entanglement experiments are simply too strong to be explained any other way. Something is fundamentally different from what we assumed. The question is only, which assumption do we give up? Locality, realism, or both? If we give up realism, the idea that objects have definite properties before measurement, we are saying that the moon, at the quantum level, does not have a complete description until something interacts with it. Its constituent particles do not have definite spins, definite positions, definite properties of any kind until a physical interaction forces a commitment. This does not mean the moon disappears when you look away. The moon is made of an astronomically large number of particles, all constantly interacting with each other and with light and with gravitational fields, all constantly being measured in the physics sense. The moon is, in the language of quantum mechanics, permanently, comprehensively, unavoidably observed. But the principle holds at every scale. What makes the classical world classical is not that it is immune to quantum indefiniteness. It is that it is so thoroughly entangled with its own internal interactions that definite properties emerge constantly and relentlessly from the quantum substrate. But here is the terrifying edge. Push that logic back far enough, and you arrive at the early universe. A universe in which, for the first tiny fraction of a second after the Big Bang, there were almost no interactions. A universe in which quantum fluctuations, genuine quantum indefiniteness, seeded the density variations that eventually became the large-scale structure of the cosmos, the clusters of galaxies, the cosmic web of dark matter and gas stretching across hundreds of millions of light-years, the very arrangement of matter in the observable universe. All of it traces back to quantum fluctuations in the early universe, to events that were, by any rigorous physical definition, indefinite, to possibilities that collapsed into specific outcomes. The universe we live in, with its specific arrangement of stars and planets and the particular location of every atom in your body, is, in a very real sense, the result of quantum rolls of an inherently undetermined cosmic dice. Then consider what this means for causality. For centuries, the defining dream of science was determinism, the idea that if you knew the position and velocity of every particle in the universe at one instant, you could in principle calculate the entire future of everything. Laplace's demon, the clockwork universe. It was never truly achievable in practice, but it was a philosophical comfort. Underneath the chaos of daily experience, the reasoning went. The gears of the universe mesh in perfect order. There is no true randomness. Everything that happens was always going to happen. Quantum mechanics demolished this dream. The outcome of a quantum measurement is fundamentally random in the strongest possible sense. Not random in the way a coin flip is random, where the outcome is in principle determined by the initial conditions, just too complex to calculate. Genuinely, irreducibly random. No additional information, no hidden variable, no deeper physical theory can predict, even in principle, which slit the photon will end up at, or which way a measured electron will spin. The universe contains events with no prior cause sufficient to determine their outcome. The strict causal chain from past to future has gaps in it, and those gaps are not gaps in our knowledge. They are gaps in reality itself. For free will, this is a complicated gift. Strict determinism was always philosophically hostile to the idea of genuine choice. If every decision you make was already fixed by the physics of the atoms in your brain 1 billion years before you were born, in what sense is it really yours? Quantum indeterminacy opens a crack in determinism, but it replaces control with randomness, which is not obviously an improvement. True freedom of will, if it exists at all, would require something more subtle, perhaps the ability of consciousness to influence which quantum possibility becomes actual. Some physicists and philosophers have suggested exactly this. Most physicists regard it with deep skepticism. The debate is live, genuine, and unresolved. And then there is the role of the observer. This is the point where the implications become most controversial, most contested, and most riveting. What counts as an observation? What causes the wave function to collapse? The equations of quantum mechanics describe the evolution of quantum states perfectly, but they do not contain within themselves any mechanism for the collapse. The collapse is imposed from outside as a rule. When you measure, the wave function collapses. But what is a measurement? What physical process distinguishes a quantum system from a measuring device? Where does the quantum end and the classical begin? Eugene Wigner, a Nobel Prize-winning physicist, posed a thought experiment in 1961 that crystallizes the problem with almost unbearable clarity. Wigner imagines his friend in a sealed laboratory, performing a quantum measurement on a particle. From inside the lab, the friend gets a definite result. The particle is spin up or spin down. The wave function for the friend has collapsed, but Wigner is outside the lab, and from his perspective he has no information about the result. The entire laboratory, friend, particle, detector, and all, is part of one large quantum system. From Wigner's perspective, the wave function has not collapsed. The friend exists in a superposition of having measured spin-up and spin-down, two descriptions of the same physical situation, both valid, flatly contradicting each other. The friend is in a definite state. The friend is in a superposition. Both are correct depending on who is asking the question. This is not a paradox that can be wished away with careful language. Experiments have now been performed genuinely in real laboratories in 2019 that confirm the Wigner's friend scenario in a simplified quantum optical version. Two different observers can have genuinely contradictory, internally consistent descriptions of the same quantum event. The universe does not impose a single objective account. Facts at the quantum level are observer-relative. The implications of this for the concept of objective reality are severe. Consciousness enters the picture here in ways that make hard-nosed physicists deeply uncomfortable. In some interpretations of quantum mechanics, most notably in the work of John von Neumann and later Eugene Wigner himself, the collapse of the wave function requires a conscious observer, not just a detector, not just a recording device, an actual mind. Von Neumann showed rigorously that you can always extend the quantum description further. The particle, then the detector, then the electronics, then the human eye, then the neural signals. And at no point in this chain does the standard quantum formalism demand a collapse. The only thing that seems to force a definite outcome is the irreducibly subjective experience of the conscious observer. This view called the consciousness causes collapse interpretation, is minority physics. Most physicists resist it vigorously, but it has never been experimentally disproved, and the alternatives each carry their own heavy philosophical costs. No thought experiment in the history of science has lodged itself in the public imagination quite like Schrödinger's cat. In 1935, Erwin Schrödinger, one of the founders of quantum mechanics and the man whose equation describes the evolution of the wave function, devised it as a reductio ad absurdum. He was trying to show how absurd the Copenhagen interpretation was when taken to its logical conclusion. He produced instead the most famous illustration of quantum weirdness ever conceived. Here is the setup. You place a cat in a sealed box along with a tiny amount of radioactive material, a Geiger counter and a vial of poison connected to the counter. If a single radioactive atom decays, the counter triggers a mechanism that shatters the vial and kills the cat. Radioactive decay is a quantum event, genuinely random, governed by quantum mechanics, fundamentally indeterminate until measured. Before the box is opened, the atom is in a superposition of decayed and not decayed. According to the standard quantum formalism, this superposition propagates through the entire chain, through the counter, through the mechanism, through the vial, through the cat. The cat is in a superposition of alive and dead. Schrödinger intended this to be ridiculous. Cats are not alive and dead. The cat is either alive or it is dead, and the quantum superposition of the atom has nothing to do with the macroscopic state of a biological organism. But here is the uncomfortable truth. He was right about the logic, even if he thought the conclusion was untenable. There is no precise, mathematically derivable point in the chain at which the quantum superposition stops and the classical definite state begins. The quantum to classical transition is smooth, gradual, and driven by decoherence. But decoherence is not, at the fundamental level, the same thing as collapse. Decoherence explains why we do not see cats in superpositions. It does not, on its own, fully explain why there is a definite outcome at all. The many worlds interpretation resolves Schrödinger's cat the most cleanly and most disturbingly. The cat is not alive and dead in a single universe. Both outcomes occur in separate branches of reality. When you open the box, you yourself split. One version of you finds the cat alive. Another finds it dead. Both are real. Neither is more real than the other. There is no collapse because nothing is discarded. Every possibility is eternally preserved in the branching structure of a reality that is constantly, silently, proliferating beyond all imagination. The universe contains not just the branch you experience. It contains every branch that has ever been or will ever be, every choice you have made and not made, every event that happened and did not happen. All real, all equally real. This is not comfortable. It is, in a way, the loneliest idea in physics. Because if every possibility is realized, then the specific you that you think of as yourself is just one thread in an incomprehensibly vast tapestry. You are real. But so is the version of you that took the other road, said the other thing, made the other choice. The particular you that exists in this branch is not privileged. It is not the real you in any fundamental sense. It is just the one whose experiences you happen to be having. But let us set aside the vertigo for a moment and consider a thought experiment that cuts even closer to the bone. Imagine you are standing in a field at night looking at a star. The light entering your eye left that star perhaps 5,000 years ago. In the time since, perhaps the star exploded. Perhaps it no longer exists. But the light has been travelling through space for 5,000 years, carrying with it the quantum state of every photon emitted in that burst of stellar energy. Those photons have been spreading through space as wave functions, probability waves, for 50 centuries. The moment one of them hits your retina and triggers a cascade of neural signals, a wave function that was spread across a sphere of space with a radius of 5,000 light-years collapses. Instantaneously. Not in any reference frame where instantaneous is an approximation. Instantaneously, in the sense that the quantum state updates everywhere at once. Einstein hated this. He spent years trying to find an error in it. The most famous attempt was the Einstein-Podolsky-Rosen paper of 1935, in which he and his collaborators argued that quantum mechanics had to be incomplete, that there had to be hidden variables, predetermined outcomes, some underlying reality that quantum mechanics was failing to capture. The paper was one of the most influential in the history of physics, not because it was right, but because it was so precisely wrong. Bell's theorem and the subsequent experiments proved that Einstein's hidden variables were not there, not missing, not yet discovered, absent. The universe does not carry pre-assigned values for quantum properties. The incompleteness Einstein imagined was not a gap to be filled. It was a mirror reflecting the actual structure of reality back at him, and the reflection was one he never fully accepted. There is a thought experiment that John Wheeler loved to return to near the end of his life. He imagined a photon emitted by a quasar 10 billion light-years away. On its journey toward Earth, it passes a galaxy that lies between the quasar and us. The galaxy's gravity bends the photon's path, not into one bent path, but into two. The photon's wave function splits, travels along two different paths around the galaxy, and reconverges on the other side. 10 billion years of travel, two paths separated by millions of light-years, and the wave function of that single photon is still coherent, still capable of interference. It reaches Earth. An astronomer, in a moment of decision, chooses whether to observe the photon in a way that reveals which path it took, or in a way that allows interference. And this choice, made in the present moment on planet Earth, in this century, determines whether the photon travelled one path or both paths over the preceding 10 billion years. The decision does not just affect the present. It reaches back through time and participates in shaping the photon's past. Wheeler called this the participatory anthropic principle. The universe does not simply exist for observers to passively witness. In some sense, the universe requires observers to crystallize its own past into concreteness. This is not mysticism. It is a rigorous consequence of the quantum mechanical description of reality, pushed to its cosmological scale. Whether you find it beautiful or terrifying depends entirely on where you are standing. Either way, it changes something foundational, something you cannot easily put back once it has been displaced. Consider, finally, the thought experiment of the quantum suicide. You are a person with a fully loaded revolver connected to a quantum random number generator. If the generator produces a 0, the gun fires. If it produces a 1, it does not. You pull the trigger. In the many worlds interpretation, both outcomes occur. One version of you is dead. Another version is alive. From the perspective of the version who is alive, no matter how many times you repeat this experiment, you always survive, because you can only ever experience the branches in which you survive. This is quantum immortality, the unsettling logical conclusion that in a many-worlds universe, consciousness can only ever experience branches where it continues to exist. There is no version of you who experiences your own death. There are only the versions who experience every other outcome, in an endless sequence of near misses and astonishments. This is not a suggestion. It is not an endorsement. It is a consequence. And it illustrates something important about the relationship between quantum mechanics and consciousness that physicists are only beginning to seriously examine. Consciousness, whatever it is, occupies a unique position in the quantum framework. It is the one thing that the equations describe from the outside, but that we experience from the inside. It is the one thing that collapses the wave function, or does not, or branches through it, depending on your interpretation. It is the interface between the quantum and the classical, between the possible and the actual, between the mathematical ghost and the thing you are holding in your hands right now. You have now travelled a significant distance from the world of ordinary experience. Not in space, and not quite in time, but in something deeper, in the grain of what is real. And it is worth pausing here, at this point of genuine philosophical vertigo, to ask what we are supposed to do with any of this. Because the temptation, when confronted with findings this strange, is one of two extremes. The first is dismissal. Quantum effects are tiny, the argument goes. They average out. They are irrelevant to daily life. The table is solid, the coffee is hot. The train arrives or does not arrive. And none of that is affected by the fact that the electrons in the atoms composing the table do not have precise positions until measured. This is true in a narrow, practical sense. And it is also a profound failure of imagination. The table is made of atoms. The atoms are made of particles. The particles obey quantum mechanics. The solidity of the table is not a violation of quantum mechanics. It is quantum mechanics, operating at a scale where the statistical behavior of vast numbers of particles produces something that feels and behaves like a classical object. The table is not an exception to quantum weirdness. It is what quantum weirdness looks like from the outside. The second temptation is over-interpretation. Quantum mechanics is not a license to believe anything. It does not validate astrology or crystal healing, or the idea that positive thinking can cure disease by collapsing quantum wave functions in your favor. These misappropriations of quantum vocabulary are unfortunately common, and they are deeply irritating to physicists who have spent their careers working out what the theory actually says. The connection between quantum mechanics and consciousness is a legitimate open question. The connection between quantum mechanics and chakras is not. There is a difference between intellectual humility about the deepest questions of physics and the abandonment of all standards of evidence. What quantum mechanics actually demands of us is something harder than either dismissal or credulity. It demands that we hold the strangeness without resolving it, that we remain comfortable with a universe that is, at its foundation, indefinite, that we accept that the most successful scientific theory in history produces predictions of extraordinary precision, while simultaneously refusing to offer a coherent picture of what reality actually is, that we sit with the fact that the measurement problem, the deepest mystery at the heart of quantum mechanics, remains unsolved after 100 years, not because physicists are not smart enough to solve it, but because the universe has not yet yielded the experiment that would distinguish between interpretations. And perhaps that is the most profound lesson. We built science on the assumption that the universe is knowable, that the right combination of experiment, mathematics, and creative thinking will eventually yield a complete and coherent description of reality. Quantum mechanics does not refute that assumption, but it complicates it in ways that Newton and Descartes never anticipated. The universe is knowable, yes, but what we have found at the bottom of our most rigorous knowing is not a bedrock of clear, observer-independent facts. It is a shimmering net of probabilities, correlations, and contextual outcomes. A universe that does not fully commit to being until something forces it to. There is something strangely moving about this, if you let yourself feel it. The universe has been here for 13.8 billion years. Stars have burned and exploded. Galaxies have collided. Planets have formed from clouds of gas and dust pulled together by gravity. Life has arisen, evolved, and in one remarkable instance, on one unremarkable planet, developed the capacity to ask questions about itself. And the answer, after centuries of increasingly sophisticated questioning, is that reality, actual, physical, observable reality, does not exist in a complete and definite form independently of the processes of observation and interaction that we call science and measurement and consciousness. Whether the universe requires consciousness in the strong sense, whether it needs minds like ours to collapse its wave function and crystallize its history, is still an open question. The most agnostic scientific position is simply that physical interactions are sufficient, that detectors and particles are enough, that consciousness is not special in the quantum mechanical sense, but only in the sense that it is the thing doing the asking. But even this careful position leaves us with a universe that is not simply there, preformed and fully determined, waiting to be discovered. It is a universe that is, in some fundamental sense, constituted through interaction, through engagement, through the act of looking. You, right now, are part of that constitutive process. Every photon your eyes absorb is a quantum event. Every neural firing in the cascade that produces your experience of reading these words involves quantum processes. The boundary between you and the universe is not as clear as it seems. You are not a passive observer peering at a world that was already there, already fully formed, already decided. You are a participant in the ongoing, never-finished project of a universe that is still, in the deepest possible sense, figuring itself out. Physics proved that reality does not exist until you look at it. It proved this not through speculation or philosophy, but through the most rigorous experimental program in the history of science. It proved it in laboratories in Paris and Geneva and Vienna and Tokyo, with lasers and photon detectors and superconducting circuits cooled to within a fraction of a degree of absolute zero. It proved it so thoroughly that the results won a Nobel Prize. And it leaves us with a universe that is stranger, more intimate, and more alive with contingency than anything Newton dreamed of. The double-slit experiment is run every day in physics laboratories around the world, by undergraduates and Nobel laureates alike, and every single time the result is the same. The particle goes through both slits. The interference pattern builds up dot by dot. The universe refuses to commit until it is asked. This has been true since the first photon was ever fired, since before any human being existed to fire it, since before there were any photons or slits or laboratories or any matter at all. It is not a quirk of our apparatus. It is not an artifact of our ignorance. It is the architecture of what is. And so we return finally to where we started. You are reading this. But a moment before you began, before your attention engaged with these words, they existed only as ink or light, as a configuration of matter with the potential to become meaning. The transformation from potential to actual, from the quantum to the classical, from the possible to the experienced, is the transformation that the universe performs trillions of times per second in every cubic centimetre of space, in every atom of your body, in the continuous act of physical reality assembling itself from the foam of quantum probability. You are not a witness to this process. You are not external to it. You are it. You are the universe looking at itself, and the act of looking is not incidental to what the universe is. It is, at least in part, what the universe is for. That is not poetry. That is physics. And it is the most extraordinary thing that the human mind has ever discovered about the world it finds itself in. A world that, it turns out, finds itself in the human mind in equal and inescapable measure.